There we go. Okay, I think we're recording now. All right, so number one, let's increase the view. All right, so as you know the story, we're going to have a function f on an interval. In this case, they say it's 1 to 3, and we're going to break this into 3 equal subintervals. And again, this assignment is already open for you, so we can go through this together and knock this homework out together. The floor will be open for questions. I can always pause the recording if you have a question. We want to break this into 4 pieces. Delta x is the length of each piece, and that is given by the formula b minus a over n. In this case, it's going to be 3 minus 1 over 4. 2 over 4, 1/2. So what are we talking about? 1 1/2, 2, 2 1/2, 3. But in general, 1 over 2. List the grid points. List the grid points x0, x1, x2, x3, and x4. So we're talking about, this is x0, x1, x2, x3, and x4. 1. Hopefully you can put decimals. 1.5. 2, 2.5, and 3. If I'm using the left Riemann sum, we're talking about, in this subinterval, I would use 1. In this subinterval, I would use the left endpoint. So you're just picking the left endpoint for each one. 1, 1.5, 2, 2.5. For the right endpoint method, you would be using 1.5, 2, 2.5, and 3. The midpoint method, we need to find the midpoints of these. So I've got 1, 1.5, 2, 2.5, and 3. And so now in these places, the midpoint method says use the midpoint. And so I need this place, which is 1.25. And this one is 1.75. And this one is 2.25. And this one is 2.75. .25, 2.75. Okay. Floor is open for questions about that. Left endpoint method, right endpoint method. Again, having 4 intervals, subintervals that we're making, and then picking the points according to the method. Left, right, midpoint. If you need to practice these, you can go to the study plan and go to section 5, chapter 5, section 1, problem number 11. We'll give this one its own page. We're going to approximate the left and the right endpoint method. We'll put it here. We got some values here. The left Riemann sum, we're going from 0 to 5, 10 pieces. Each interval should be of length 1/2, and it looks like this is by half, so that's nice. So 5 minus 0 over 10 is 5 over 10. That's 0.5, and this is already in 0.5 interval, so that's good. So then the left Riemann sum would be equal to, so let's do the left endpoint method. By the way, Riemann is a mathematician back in the day. The left endpoint method would be, well, the length is going to be 1/2 times, and then on the interval 0 to 0.5, you're taking the value at 0, which is 3, plus 1/2 times the value at 0.5, which is 5, plus 1/2 times 11, and so forth, right? All the way up until 1/2 times 4. Now we know that they all have 1/2 in common, so you're just doing the length, and then it's 3 plus 5 plus 11 plus 14 plus 24 plus 36 plus 22 plus 15 plus 8 plus 4. 8, 10. Whatever that number is. And then the right endpoint method, you go up here, and let's just be clear about what we're doing, right? So then in this interval from 0 to 1/2, you take the right endpoint. So then you would just shift everything. 1/2 times 5 plus 11 plus 14 plus 24 plus 36 plus 22 plus 15 plus 8 plus 4 plus the right endpoint at the end is 1, or whatever that number is. And then to give you both of those approximations. Give you a second to do that, fill that out for your problem, and then we will move on. Similar question here, but now phrased in some context. Here we got a table, and I'm giving you the velocities, and now they're asking us about the displacement. We should make a comment here about that. So we know that when I have s of t is displacement or distance, let's do it this way, distance, then we know that the derivative of s is the velocity. But there's now something that we know because of the fundamental theorem of calculus. We know that the integral from a to b of v of the velocity is going to be equal to the integral from a to b of s prime of t. And we know from the fundamental theorem of calculus that the area under that is equal to the difference in the endpoints. The antiderivative of s prime is just s. And so this would be s of t evaluated from a to b, and then this is just s of b minus s of a, which is just the displacement. It is the difference between where you started and where you ended. The difference between where you ended and where you started. So when they say find the displacement, they're simply saying find the area under the curve. Right? So displacement means area under the curve. Right, sketch a smooth curve passing through the data points. All right, process of elimination. At 0, it needs to start at 50. At 0, it needs to be 50. At 0, it needs to be 50. At 2, it needs to be 75. At 2, it needs to be 75. They both do that. At 1, it needs to be 50. At 1, it needs to be 50. Okay. It's checking 0, 1, and 2. Gets rid of all the stuff. Find the midpoint. Riemann sum approximation to the displacement on 0 to 2 with n equals 2 and n equals 4. So we'll do a couple of these, right? So then we'll take this. So all we're doing is approximating with rectangles like we've been doing over the last couple of classes. And now we've just been given a table. All right, n equals 2. So n equals 2 means that b minus a over n is 2 minus 0 over 2. So that's 1. So we're talking about an interval from 0, 1, and 2. And now we want to do the midpoint method. And so I want to know the value at 0.5 and the value at 1.5. So the midpoint formula is going to be delta x, which is 1, times the sum of the value at 0.5. So let's write it. It's 1 times f, in this case it's v, 1 times v at 0.5, because they wanted the midpoints, plus v at 1.5. That equals 1 times the value at 0.5 is, we were going 50 miles an hour at 0.5, and then at 1.5 we were also going at 50 miles an hour. 100 miles. Okay. Now, how is it that we get miles here? It is because 1 is in hours, right? So this was hours, this was hours, this is an average, this is hours. And so this is a 1 hour out here times 100 miles per hour just makes 100 miles. So that is an approximation to how far you are from where you started. If we do with 4, when n is 4, then we're talking about b minus a over n, 2 minus 0 over 4, 1/2. And so we need to go from 0 to 0.5 to 1 to 1.5 and then to 2. If we're doing the midpoint method, they want us to then use the points that are halfway between these. And thankfully, the chart gives us those. So 0.25, 0.25, 0.75, 1.25, and 1.75, right? And all those values are given. And so it's going to be 1, which is b minus, oh, I'm sorry, it's not 1, it's 1/2. It's 1/2 times v at 0.25 plus v at 0.75 plus v at 1.25 plus v at 1.75. And we have all those numbers. So we've got 50, 60, 50 plus 60 plus at 1.25 is 65 and 55. Right, so that's 120 plus 110, 230, 1/2, 230. As we know, this is a better approximation, 115 miles away from where you started. Questions on that? Again, just breaking up the interval. So they'll give you the data table. They'll tell you how many rectangles they want, and then they'll tell you the method that they want. And so I always tend to just draw a number line and then break up the pieces into how I need to break it up, and then select how we want the points. And then it's always going to be just adding it up times the width of the interval. Okay. 100 and then 115. Consider the velocity function for an object moving along a line shown in the figure. Describe the motion of the object over the interval 0 to 10. All right, so this is the velocity. Use the geometry to find the displacement of the object from 0 to 2. Use geometry to find the displacement of the object from 2 to 8. And assuming the velocity remains 20 meters per second after 8 seconds, what's the displacement function between 0 and t and any time t greater than or equal to 8? So we'll grab this here. Great. So first thing we're going to do is translate. So, well, first of all, let's get the description here. So, oh, and I think I want to zoom in just a little bit so we can investigate this. So the first thing we'll say is that it looks like this is the velocity. So it looks like the velocity is increasing. So you're speeding up from 0 to 1 second. Right, so on the interval 0 to 1, you're speeding up. The velocity is constant from 1 to 2. I'm sorry, longer than that, 1 to 5. Right, constant speed. Then it looks like you're slowing down from 5 to 8. And then 8 to 10, or 8 to infinity, you're constant. Right. So I will answer those questions. The other translation we'll do is that when it asks for the displacement, for this it's going to be the distance. It's the same thing because you're always moving to the right, right? So the velocity is always positive. It's not going under the x-axis. Either way, it's just the area under the curve. So when we think about displacement, we'll translate as displacement simply means the integral from 0 to 2 of v of t dt. In this case, that does just mean the area. Right? So then all we're trying to do is find the area under this curve. Well, note that looking at the scale, this is by 5s and these are by 1s. Right? So each block is 1 by 5, and so each block is 5, and that might be able to help us calculate these areas pretty nicely. So from 0 to 2 means I need this area here, which is the sum of a triangle and a rectangle. And so that first triangle is 1, has a base of 1 and a height of 30. So that's equal to that triangle, which is 1/2 times 30, plus, and then that other, this rectangle here, looks like it is just 1 by 30. 45. Units are in meters. So after 2 seconds, you are 45 meters away from where you were at the beginning. Your displacement is the area under the velocity curve. your displacement is the area under the velocity curve. In this case, it's the area, but in general, it's the integral from 0 to 2. From 2 to 8, we'll roll the same way, and now we got these boxes. I am worried about maybe this. Maybe we'll stop here. We'll calculate the area of this trapezoid. We'll need the area of that trapezoid, right? So from 2 to 8, we'll put it in green. So we'll go from 2 to 5. From 2 to 5, that is just 3 by 30. So when we go from 2 to 8, let's just be clear about this. So from 2 to 8, it's the integral from 2 to 8 of v of t dt, and we'll use some integral properties. That's the same as the integral from 2 to 5 of v of t dt plus the integral from 5 to 8. And again, in this case, all these things are just the areas under the curve. So from 2 to 5 again, that's 3. The height is 30. That's 90. And then now we need the area of this trapezoid. The area of a trapezoid is 1/2 the height, although the height's on this side now, so the height's 3, and then times the average of these heights. That's 20. I'm sorry, the sum of these heights. That's 20 here and 30 there. 30 plus 20. The area of a trapezoid. 90 plus 1/2 times 3 times 50. 90 plus 75. 165. You're now 165 away. Between 2 and 8, you're 165 meters farther from 2 when you're at 8. Stays constant at 20 meters per second after 8. What is the displacement function between t equals 0 and any time after that? Well, we're going to add up all this stuff. I think we have it now. We have the 45 we had at the beginning. It was 45, right? 45. And then you go another 165. And then now, the function that's going to tell us how far we are, well, I'm going 20 meters per second for every second after 8 seconds. Then that is going to be 20 times t minus 8 for every second after 8 seconds. So for instance, when t is 9, you get 20 meters. When t is 10, you get 40 meters, right? So you just plug in 9, 8, 9, 10, 11, 12 into this. 210 plus 20t minus 160. 20t plus 50. That'll tell you where you are, how far you are from where you started after any time at all. After 8. This is after 8 seconds. Take any questions there. Great. Number 5, use geometry, note rectangles, to figure out the integral from -4 to 1 of 2x plus 4. Choose the correct graph below. We know 2x plus 4 is a line. It needs to hit the y-axis at 4 and have slope 2. I'm liking A. Let's see here. Oh, no, but wait. We're going from -4 to 1. So I need to start at -4. Nothing over here is shaded at -4. I'm not liking that. -4 to 1. This is supposed to hit the axis at 2, -2. So I'm really liking this one. This hits the axis at -2. It's not that one. Hits the axis at -2. It's only that one, right? So now, let's take this picture. I've got 2x plus 4. It's 1, 2, -2, 1, 2, 3, 4. It's doing this. But I care about the net area from here, -4 to, what was it? -4 to 1. And so at 1 to up here, right? When you plug in 1, 2x plus 4, right? When you plug in 1, that's 6. 1, 2, 3, 4, 5, 6. Right? So it's this net stuff here, which whatever we do, we're going to get that. And here, we're just got to keep track of the signs. So at -4, the value is 2 times -4 plus 4 is -8 plus 4 is -4. So this is 1, 2, 3, 4. So this is -4. Right? And so now I think we are ready. I'm going to add up this area and this area, keeping in mind the signs. So the height here is -4. The width is 2. And so we're talking about -8. And it's half the base times the height. So this here, the integral here, is -4. For this one here, the distance here is from -2 to 1 is 3. The height is 6. Half the base times the height. Half the base times the height, 1/2 of 18, 9. The integral here is the area between the graph and the x-axis. That's 9. The integral here is -4. Right, because it's 4 by 2, yeah. And so I'm going to add them. The integral is 5. Now, as we learned last time, we could use the fundamental theorem of calculus to take the antiderivative, but we can also just get it by using the geometry, finding the areas between these two triangles, one positive and one negative. So one of the examples we had earlier, when we had the integral from -9 to 0 of the square root of 81 minus x squared, we had said that, oh, if we square both sides, that's y squared plus x squared equals 81. That is a circle centered at the origin with radius 9. We're going from -9 to 0, and so we definitely need to be on the left-hand side of the x-axis. And this is positive square root of 81 minus x squared. -9 to 0 of the positive square root. That's a circle, that's part of a circle of radius 9. So the area of the entire circle is pi r squared. The area of the whole thing is 81 pi. And of course, I want the area of this quarter of it, 81 pi over 4. The graph of f is shown in the figure to the right. Let a of x be the integral from -2 to x of f of t dt. Let's see if we can zoom on this a little bit. Capital F of x is the integral from 4 to x of f of t dt, and these are two area functions. So let's just be clear. A starts at, this goes by 2, so A starts here. Oh, we need a much thinner bar. So A starts here, -2, and starts measuring area. And then F starts at 4 and starts measuring area. Okay, great. And they tell us the areas in these places. All right. They want to know a of -2. Let's be clear. A of -2 is the integral from -2 to -2 of f of t dt. Well, we could go back and find our integral rules, but we know that if I wanted to find the area from one place to itself, that's a bunch of nothing, right? Because that's just the integral, and you don't even move any to the right at all. There's no area there. F of 8 is the integral from 4 to 8 of f of t dt. Going to the graph, from 4 to 8, that's this. The area is 8, but the integral is -8 because all that stuff is below the x-axis. The area is 8, but the integral is -8 because the integral takes into account what the sign is. A of 4 is equal to, we're measuring the area from -2 to 4. The integral from -2 to 4 of f of t dt, looking at -2 to 4, that's all of this. Well, this side is 7, that side 16, 23. Everything's positive. All right, so I just went from -2 to 0 and then 0 to 4 and added those two. F of 4, they're trying to get us. F of 4 is the integral from 4 to 4, and I don't need to say anything else. 0. A of 8, let's go back down here. Oh, I can fit it in here, so we'll put it here. A of 8 is the integral from -2 to 8 of f of t dt. Is that the whole thing? Looks like that's the whole thing. So I've got, let's clear this thing. That means I've got this 7 plus that 16 minus that 8. 15. Seven plus 16 minus 8. So open for questions. So again, the integral just measuring the net area under the graph, between the graph and the x-axis. Fundamental theorem of calculus. Let's just figure out what this is. This is equal to, so it says, when it says use the fundamental theorem of calculus, that means that we get to find antiderivatives, plug in the endpoints, and subtract. The antiderivative of x squared is 1/3 x to the third. The antiderivative of 2x is x squared, and the antiderivative of -3 is -3x. We'll plug in -3, 1, and subtract. We'll plug in 1 and -3 and subtract. So then this is 1/3 times 1 cubed plus 1 squared minus 3 times 1, and then minus 1/3 times 3 cubed. I'm sorry, that's times -3 cubed plus -3 squared minus 3 times -3. Right? So then that's going to be 1/3 plus 1 minus 3 minus negative 27, negative 9, plus 9, plus 9. 1/3 minus 2 minus 9. 1/3 minus 11. 10 2/3. Negative 10 2/3. Negative 32/3. Right, so just playing with all those fractions. From negative 3 to 1, looks like it's this one. First of all, the fact that we got a negative here, if we believe we've done this right, then it cannot be these, right? Because those areas look clearly positive, right? And we also know it can't be that because this parabola is definitely opening upwards, right? So we knew this couldn't be it because the area looks positive and we should have stuff that's at least adding up to something that's negative. So we know we can find out where these hit the axis. So we've got x plus 3, x minus 1. So this should hit the axes at negative 3 and positive 1. And that would be not that one, but this one. You can also just graph it in Desmos as well. Evaluate the integral. Again, just fundamental theorem of calculus. We'll use this one. We'll write these as powers first. 1 to 4 of 5x plus x to the 1/2 power. We'll get to the business of finding the antiderivative. Bunch of fraction nonsense going on over here. 5/2 x to the second plus 2/3 x to the 3/2. Evaluate it from 1 to 4. Add 1 to the power gives you 3/2, and then flip the number that you have as the power. Plugging in 4, 5/2 times 4 squared plus 2/3 times 4 to the 3/2 minus 5/2 times 1 squared minus 2/3 times 1 to the 3/2. 16, 8, 40. 4 to the 3/2. Square root of 4 is 2. 2 to the third is 8. 16/3. Minus 5/2 minus 2/3. Whatever that number is, right? So then we've got 80/2 minus 5/2 plus 14/3. 75/2 plus 14/3. And you can just figure out whatever that number is. Fundamental theorem of calculus, antiderivative of e to the 2x is 1/2 e to the, we'll keep the 4 here, 1/2, 4 times 1/2 e to the 2x, evaluate it from 0 to 5. Plugging in the 5, 1/2 e to the 10 minus 4 times 1/2 e to the 0, 2e to the 10th minus 2 times 1, 2e to the 10th minus 2. Finding antiderivatives. Find the area between the curve and the x-axis over the indicated interval. Let's just be clear about what we're talking about. We're talking about 8/x 8 over x, we'll bring this home. There it is. And they want us to start from 1 to 10. So from 1 to 10, they want this area. From here, x equals 1. And then x equals 10. Right? So the area between those two lines. Let's figure out what that area is. Of course, that means we want the integral from 1 to 10 of 8 over x. This is equal to 8 times the integral from 1 to 10 of 1 over x, and now we need the antiderivative of 1 over x, and that, the function you take the derivative of to get 1 over x is the natural log. That's 8 times the natural log of 10 minus the natural log of 1. I'm working with my my college algebra class. They just learned that the natural log of 1 is 0. 8, the natural log of 10. That's the area under that curve. Question there. Area of the region bounded by f of x equals x times x plus 2 times x minus 3, and the x-axis on the interval -2 to 3. Let's do it. X times x plus 2 times x minus 3. X times x plus 2 times x minus 3. On the interval, is it -2 to 3? Looks like it is. Find the area of the region. Okay, so now, let's get that picture. We got something like that. We'll zoom out. So here we have to worry about signs, right? So then I'm going to do something like this, and we're going to get a new page for this. We're going to bring this over here like this. Oh, and we'll do that. We'll leave that there, and then we'll go and we'll bring the question. Let's just be clear about what they want. Right here. Okay, so then they want, great. We'll zoom out. All right. So what they want to know, this area, well, let's use a different color. They want to know, they want to know this area. And then plus this area. So we're going to find them separately, right? So you could then ask, well, wait, why don't we just do the integral? Here's what some people are going to do. Why don't we just do the integral from -2 to 3 of this function? Why don't we just do that? Well, that's not going to answer this question, right? What the question is asking is, what is the area of this region, of the green region plus the yellow region, all positive? The integral is going to make this stuff negative, and so when you calculate this number, it's going to be the negative of this area plus the green area. When in fact, this is asking, well, what is the positive of this area plus this area? Okay, so when we do these separately, I'm going to leave this alone and just calculate the integral because it's going to give me the positive thing. But then to calculate what I want this area to be, I'm going to change the signs and then calculate it. All right, let's see. Okay, so now looking at the picture was helpful because now I want to take the integral from, that's 0, -2 to 0 of x times x plus 2 times x minus 3. So the only other thing that's been annoying is that we've got to multiply this whole thing out in order to get a nice polynomial that we can do stuff with. All right, so let's just get what this is. X times x plus 2 times x minus 3 is equal to x times, we'll FOIL, x squared minus x minus 6. We'll distribute x again, x cubed minus x squared minus 6x. All right, so we got the integral from minus 2 to 0 of x cubed minus x squared minus 6x dx. We'll use the fundamental theorem of calculus to solve this. The integral from minus 2, let's use the theorem. This is then going to be equal to one-fourth x to the fourth minus one-third x to the third minus 3x squared, evaluated from negative 2 to 0. Plugging in 0 first gives us 0 for everything, minus plugging in negative 2 gives us this. Right, so this is going to be equal to negative, and that is 16 over 4, and then that is negative 8 plus 8 over 3, and then that is 4, 12 minus 12. Negative, and then that, if we put everything over 3, that's, let's do this, 8 over 3 minus 8, negative 8 over 3 minus 24 over 3, positive 16 over 3. That is the area of the green part. We need the area of the yellow part, so either we just need to put a minus sign somewhere. So the area of the yellow part, we just need to put a minus sign in front of the integral. It's the integral from, in this case, it's 0 to 3 of the same function. X cubed minus x squared minus 6x. What's nice, of course, is that the antiderivative is exactly the same. I want to make sure I've written it right. So then this is going to be equal to negative, and then it's going to be 1/4 x to the fourth minus 1/3 x to the third minus 3x squared. And again, now this is evaluated from 0 to 3. This is equal to minus, and then that's going to be plugging in 3, 81 over 4 minus 9 minus 27. I'm sorry, 27. And then minus, when you plug in 0 into all of that, you get 0. So this is minus 81 over 4 minus 36 minus 81 over 4 minus 4 times that, 144 over 4. Yep. And this is equal to negative, and that's negative 63 over 4, which is positive 63 over 4. So the integral from 0 to 3 is negative 63 over 4, but the area of the yellow part is positive 63 over 4. Adding that to the green part is 16 over 3, and that's the answer, 63 over 4 plus 16 over 3. Find the common denominator and get the answer. Similar question like we answered before. Giving us an area function. We're just watching closely. A of x is starting from 0 and is measuring the area through the whole thing. We're going to assume that this is a quarter circle. Looks like it is. And got some triangles there. Let's see if we can figure this out. It looks like it's going by 2's. Let's see what A of 4 is. So A of 4, oh, let's use a different marker. A of 4 is the integral from 0 to 4 of f of t dt. It's the area from 0 to 4. Oh, that looks like this, right? But it's the integral here. And so again, that's a quarter circle of radius 4. So the whole circle is pi r squared, would be 16 pi. And this is just a quarter of it. And so it would be 4 pi. And of course, all of that stuff is under the x-axis. The integral from 0 to 7 of f of t dt, well, I'm going to need the integral from 0 to 4, which I have, and then now I need the integral from, let's write it, this is the integral from 0 to 4 of f of t dt, and now I need the integral from 4 to 7. Alright, so 4 to 7, 7 is like here, right? That looks like that's 3, right? So that looks like the base is 3, so 1/2 the base, and looks like the height is also 3, 9/2. So this piece is 9/2, this piece is minus 4 pi, 9/2 minus 4 pi. Negative 4 pi plus 9/2. We'll keep that in mind, right? So that's negative 4 pi. That's 9/2. You might imagine what they're going to do to us. All right, to 10. That looks symmetric, so this looks like another 9/2. Let's just double check that. 4 to 10, 6 by 3, half the base times the height is 9. Great. So the integral from 0 to 10 of f of t dt is going to be that negative 4 pi plus that 9/2 plus another 9/2 up until 10. 18, I'm sorry, not 18, 9 minus 4 pi. And I think for the game, we're going to add this little piece here from 10 to 12, half the base times the height, 1/2. The base is 2, 10 to 12. The height looks like it's 1. And it's under the x-axis. So that area is 1, but the integral is actually negative 1. 8 minus 4 pi. Tack on a negative 1. Right? So we started off at negative 4 pi, added some positive area, 9/2, added some more, 9/2, and then subtracted 1 at the end. All right, that is it. All right, I'll stop recording there.